Okay, so we arrived to the section of mechanism of hormone action in our chapter 1. So here in this rest of the chapter, we will be interested by the characteristics and the classification of receptors of the hormones. So we will be studying these. And we saw already this slide, which is a general slide of the mechanism of hormone activity. Just keep in mind that for each hormone to be able to act on its target tissue, it needs a specific receptor that is going to recognize specifically this hormone. And then it should change something inside of the cell in order to have a biological action at the end of this cellular communication. Okay, so I need a change in the biological activity of the target cell. So first we will talk about some characteristics of physiological receptors. The physiological receptors have specific characteristics, which are first of all the specificity. Each type of receptor binds only one specific hormone or a small number of closely related hormones, which is a rare case. At normal physiological levels, each hormone interacts only with its own specific cellular receptors. An example is oxytocin and vasopressin that are related in structure but bind to different receptors. So what we want to say from all this paragraph is to talk about the specificity of the receptors toward their ligands. And to have an idea about this, you have to imagine how many proteins there are in the cell and outside of the cell, at the surface of the cell. If there is no specificity, whatever molecule could interact with another one and have an effect. No, here what we want to say is that the recognition, okay, of the target cell is going to be done through the specificity of the receptors that bind only to one specific hormone. Each receptor bind to one specific hormone. العكس مش صحيح. A hormone can bind to more than one receptor. اوكي الاكزامبل هو مثلا اي ار الفا واي ار بيتا تبع الاستروجين. But the idea هون انه each receptor is going to specifically bind to one hormone or a small number of closely related hormones. So usually it's like one receptor for the hormone, but في عندي some cases where I do have a receptor can bind to more than one hormone to that these hormones are going to be related in structure probably. Okay, so for example مثلا اذا بناخذ الادرينرجيك ريسبتور الفا في عندنا الالفا 1 الالفا 2 البيتا 1 والبيتا 2. الادرينرجيك ريسبتورز هن الريسبتورز that are going to be able to bind to catecholamines يعني للادرينالين. اوكي so في عندي الادرينالين وعندي النورادرينالين او الابينفرين والنورابينفرين, right? So both of them are very closely related in their structure, and that they are able sometimes to use the same receptors. Okay, so sometimes but بضل في عندي شوي affinity that is going to be different from one to another of these hormones to the receptor. Okay, so لكن اللي أنا بدي أعرفه إنه usually what I say is that one specific hormone or receptor would in fact bind to one hormone or a closely related hormones. Okay, and at normal physiological levels, each hormone interacts with its own specific cellular receptor. The example of oxytocin and vasopressin that is given here is in the idea to say that these two hormones are very related in their structure. They are both composed of they are يعني oligopeptide and a very short peptide amino acids, and they have a ring structure because they have a disulfide bond. So في عندي structures تبعهم اثنيناتهم are very related. The difference is very tiny in between them, like at the level of the amino acids, and still with all this oxytocin has its own receptor and vasopressin has its own receptors that are completely different at physiological concentrations in the blood. Specificity is capital for pharmaceutical industry to provide hormone analogs. So this specificity is of great importance, in particular when we are developing drugs in pharmaceutical industry, because those drugs could be receptor agonists, لأنه I need hormone analogs, either that these hormones can be agonists, which means that they are going to bind and mimic the action of the hormone, and this would be in the case when you have a lack of a specific hormone, or they can be receptor antagonists, bind and prevent the activation of the receptor, and in this case I would like to compete with the real hormone and in order to reduce its effect. Okay, so if I want to induce the effect of the hormone, I need an agonist which is going to bind and mimic the activity of this hormone on its receptor, or in the other case where I need to block the activity of this hormone, I will use an antagonist. In both cases, these hormones should be hormone analogs, and by this they should be able to bind to the receptor, either to stimulate it or to deactivate this receptor. Okay, so this is important for you to know the definitions of agonists and antagonists. The second characteristic of the receptors is their high affinity toward their ligands, of course. The high affinity toward their ligands, the binding of an hormone to its receptor occurs always with high affinity. I do have a high affinity between the receptor and its hormone. So I do not really need a lot of concentration of the hormone to have an activity because I do have a high affinity. So the binding is a consequence of non-covalent interaction between, of course, the receptor and its hormone, as you can see here in this reaction. The interaction can be ionic, hydrophobic, or van der Waals attractions. The affinity of a receptor for a ligand is derived from the extent of these interactions. So the more I have extent interaction between the receptor and its ligand, then the affinity is going to be greater, or it's going to be lower if I don't have a very high extent of these interactions between the two molecules. So remember that when the receptor is going to bind to its hormone, so this is the total number of receptor R, well, hormone, this is the reaction in fact. A receptor plus hormone is a reversible reaction that is going to give me the molecule or the complex hormone receptor. So in a reaction, this reaction can go to the right in order to produce this complex, or can go to the left in order to do the dissociation. Okay, and this is what is happening all the time, going to binding and separate, binding and separate. Okay, until we arrive to a equilibrium. So this reaction is characterized by what we call a dissociation constant Kd. Okay, and this Kd is the value that we are going to use to describe the affinity of a receptor for a hormone. Okay, for each couple hormone receptor, كل couple hormone receptor عنده a dissociation constant Kd that is different from a different couple. كل couple hormone receptor عنده a dissociation constant that is going to be different from another couple. For a receptor with high affinity for the hormone, for a receptor with a high affinity for its hormone, then it has a low Kd value. Or if a receptor has a low affinity for its hormone, then I have a high Kd value. The higher the affinity of a receptor for hormone, the lower is the Kd. And you will see why. Why? Donc, dissociation constant, okay, it is the constant that is going, by which we are going to describe the affinity between the couple hormone and the receptor. And this dissociation constant is usually very low. ليش؟ لأنه هي بحد ذاتها الهرمون والريسبتور interaction is يعني الافينيتي تبعهم هي عالية. So anyways the KD is going to be very low. The more the KD is lower, the more the affinity is higher, and vice versa. Okay. A typical hormone receptors KD values vary in the range of 10 to the minus 11 to 10 to the minus 8 molar. Okay, this is the affinity value, the KD values for an hormone with its receptor. KD is specifically defined as the concentration of the hormone at which 1/2 of the receptors are bound. Okay, so KD, it also corresponds to the concentration of the hormone at which half of the receptors are bound. So هالشي بيعطيكم فكرة why إذا كانت ال KD lower ليش عندي affinity أكتر. إذا أنا عم قول I have a KD of 10 to the minus 11 for example. So this is a very low KD. So then the affinity is high because this KD, it corresponds to the concentration of the hormone. Okay, how many molecules of hormone do I need in order to occupy half of the receptors, at which 1/2 of the receptors are bound, in order to occupy half of the receptors. مثلا إذا عندي أنا 100 receptor 100 and I need 10 to the minus 11 mole of my substrate of my hormone يعني, to occupy half of the receptors. But so I need very low amount of this hormone. This means that I have a high affinity. If I compare this couple of hormone receptor to another couple of hormone receptor that has a KD value of 10 to the minus 6, for example, then in this case, I need 10 to the minus 6 mole of the hormone in order to occupy half of the receptors. I need much more than in the first couple. So this means that the affinity is low. Okay, so هيدي الديفينيشن تبع KD عندها more than one definition. Like, you just keep in mind, and of course they are related. Okay, so أول شيء بسميها dissociation constant of the reaction, and I will use it to describe the affinity between this couple of hormone and its receptor. And the relationship is that the higher the affinity of a receptor, the lower is the KD, because the KD is defined as the concentration of the hormone that will occupy half of the receptors. إذا الكونسنتريشن تبع الهرمون يلي will occupy half of the receptor is very low، معناتها أنا عندي high affinity بكونسنتريشن كتير قليلة، فيني أنا ب 50% من الريسبتور يصيروا occupied. If another couple of hormone receptor needs much higher hormone concentration in order to occupy half of the receptors, then in this case the affinity is lower. Generally, the basal concentration without stimulation of hormone in blood is lower than the KD in order to prevent saturability after stimulation. Okay, so this means that when a hormone is not under stimulation, so it is at its basal concentration without stimulation in the blood, لأنه every hormone will be present in the blood even at very low concentration, even without a stimulation. When it's going to be stimulated, of course, this will induce a peak of the concentration of the hormone in the blood for some time, depending on its half-life. So generally, the basal concentration of the hormones in the blood is lower than the KD. So usually, إذا ما في عندي stimulation, the hormone in the blood is very low concentration, lower than the KD, of course. ليش؟ يعني أكيد مش هأعطي أنا من الأساس ديجا concentration of hormone that will occupy half of the receptors from the beginning. لا، وإلا ما بيكون في عندي a range أنا أقدر أشتغل فيه in order to prevent يعني saturability after stimulation، يعني حتى ما يصير في عندي دغري saturability سريعة للreceptors إذا عملت stimulation. So this is to keep in mind that the basal concentration is lower than the KD, يعني lower than the concentration of the hormone that is needed in order to produce to occupy half of the receptors. Before going to the rest of the characteristics of the hormones, I have here a slide, slide number 74 and 75, which are going to explain, 3 slides in fact, which are going to explain better this idea about the affinity. So here I put for you some kinetics of the reaction between the hormone and its receptor, some definitions. So let's go through them together a little bit rapidly. So the interaction between the hormone and ligand, the hormone ligand and its receptor are governed by the laws of the mass action. So the concentration of the hormone plus the receptor is going to give me the HR. Chi plus 1 and chi minus 1 are the rate constant for the HR formation and dissociation. So this chi plus 1 is K plus 1 is the rate constant for formation, and K minus 1 is the rate constant of dissociation. Okay, so I have a constant for the association, formation of the complex, and another constant for its dissociation. And each time, of course, it's going to be different, and not necessarily that K plus 1 is equal to the K minus 1. No, they can be different. Until I put this reaction in a very long time to an infinite time, and then I arrive to the equilibrium. And at this equilibrium, I have concentrations that are kind of constant concentrations. Okay, and I can say that at the equilibrium, K plus 1 HR is equal to K minus 1 with the complex HR. From this, you can define the KD. The KD, as I said from the beginning, is the equilibrium dissociation constant. KD is the equilibrium dissociation constant, and you have another constant of association at equilibrium, which is the Ka, okay, which we do not need in our case here. Okay, so the KD is the equilibrium dissociation constant that we are using to define the affinity of the hormone receptor interaction. Now, if you take into consideration, okay, so the KD من هيدا الرياكشن you can أول شيء KD is defined as the K minus 1 على K plus 1 بينما K constant of association at equilibrium is equal like هي inverse of the KD, which means that it's K plus 1 على K minus 1. Good. Now, if you take from this here, if you take if you consider that the total receptor concentration هي R0, قديش أنا عندي receptors R0 total 100 receptor مثلا, HR it's going to be equal to the occupied receptor by the hormone plus the free receptors. HR هن occupied and R هن free receptors. Okay, so if I do the sum of both of them, I will get the R0, which is the total receptor concentration. Now, if you replace in this equation, if you replace R0 equal HR plus R, and you write it under this way, the concentration of the occupied over the concentration of the free hormone as a function of the occupied hormone, then it gives you the Scatchard equation. Okay, this is the Scatchard equation. هي ذاتها هذه اللي هون. Okay, which states that when bound over free ligand, HR هي الباوند على الفري ligand is going to be plotted against the bound ligand as a function of the bound ligand. The slope of the line, okay, it's defined by 1 over KD, يعني y equal AX plus B, and y, you have the y is the bound over the free ligand as a function of the bound ligand, which is the HR. In this case, the slope is going to be the 1 over KD, and the y-intercept, for which you have the x equals 0, is equal to R0 على KD, and the x-intercept for which the y is equal to 0, then in this case is going to be R0. The x-intercept is R0. If you look على هون, maybe here in the graph is much more. لكن هون بهيدا الجراف أنا عندي two possibilities. إنه أقول I would like to plot the ligand saturation. Ligand saturation يعني أنا I'm going to see the variation of the HR as a function of the concentration of the hormone. كيف عم تتغير as a function of the concentration of the hormone. And you will arrive to a saturation. In fact, you will arrive to a saturation. Instead of having this, and more is a bit practical at the practical level, يعني بالexperimentation, you are going to plot the HR على ال H as a function of the HR, as a function of the bound receptor أو hormone. Okay, and in this case, you have a linear equation for which y equal ax plus b, for which the a is minus 1 over kd, from which you are going to deduce the kd, and the x-intercept will y-intercept, they will give you r0 and r0 over kd. Okay, of course, this is not, you do not need to go into details with all this, because all these kinetic interactions, you will see them in the course of enzymology next. Enzymology, you did already took it, right? Did you?
Yes, doctor, عم ناخد.
You are taking the enzymology now?
Yes, وهالاشياء قلناها يعني مرق عليها الدكتور مازن.
Okay, so you know the structured analysis and everything, right?
Yes.
Perfect. Good. So don't go into details, because in our case, we're not going to give you like exercises and to deduce the KD and so on. Just like know the titles, the KD, what the definition of the KD, its relationship with the affinity, how it's going to be defined as a concentration of the hormone that occupies half of the receptors. Okay. So just you have to know this. Okay. So these latest slides are just like for you to be able to better understand the definition of the KD and its relationship with the affinity of the couple hormone receptor. I go back to the characteristics of physiological receptors. The third characteristic is saturability. Cells do not possess receptors for all hormones, but rather only a limited number of receptor types, of course. Otherwise ما بيكون في عندي like target tissue for a specific hormone. The magnitude of a tissue's response to a particular hormone is determined in large part by the number of receptors that are present in those target cells. So number of receptors in the cells are important as a factor to determine the magnitude of a tissue's response to this hormone. Each cell produces a finite number of receptors, thus the number of ligand receptor complexes is limited and should reveal a saturability. In general, a cell generates between 2,000 and 100,000 receptor molecules. Okay, so here just to say إنه النمبر تبع الريسبتور بقلب التارجت tissue is important to make a correlation with the magnitude of this tissue to respond to this specific hormone, and that this number is a finite number in the target tissue, and it should reveal saturability. يعني the characteristic of saturability is one of the characteristics of the receptors of hormones. They can be saturated. And we saw this when we were talking about additive activity of two hormones. If you remember, when I said this is true, this additive activity is true if I don't arrive to the saturability or otherwise of the signaling pathway, or otherwise it's going to be saturated, and I don't have additive effect anymore. Reversibility, the removal of hormone from the target cells results in rapid decay in the effects of the hormone. So هون reversibility is between، عم نحكي دايما نحن between الهرمون والريسبتور، انه انا اذا بشيل الهرمون بيرجع هيدا الريسبتور على شكله الاساسي. So دونك هالinteraction between هالهرمون وهالريسبتور عملت a change in the conformation of the receptor. It induced something, okay? But then if I remove this hormone, this change should be removed and the receptor should go back to its initial conformation، بغض النظر عن طبعا تبعية التشينجز اللي صاروا بقلب السيل، لأنه ببعض الأحيان هالتشينجز اللي صاروا بقلب السيل لحتى يرجعوا على البيزل ستاتس ما بكفي أنا إنه شيل الهرمون من الموضوع، ولكن في other enzymes that are going to be interfering inside of the cell in order to bring it back أو in order to stop the effect of the hormone. Okay? بس هون عم نحكي بالreversibility هي على level of the hormone receptor. So the removal of hormone from target cells results in rapid decay in the effect of the hormone because the change is just like كده تذكروا there's no covalent changes بقلب الريسبتور بحد ذاته بشكل انه انا غيرت فيه شيء bond or something وتغير شكله الى نهائيا يعني. So this is reversibility. And finally, the physiologically active, the binding of the ligand to its receptor should lead to some significant physiological response in the target cell. يعني طبعا لازم هالreceptor should have a physiologically active, should bring a change inside of the cell in order to be physiologically active. Okay, لكن هو هن 5 characteristics of the receptors يلي هن لكينا specificity, high affinity, specificity, high affinity, saturability, reversibility, and physiologically active receptors for the hormones. Now, if we go and try to classify the receptors. Now, in this classification of receptors, a lot of information, you already know it from the cell physiology course, but still we do have, you know, like new information. So if I want to classify the receptors, here they are going to be classified into 5 types of receptors. طبعا هون نحن عم نعتبر انه هو كلهم are surface receptors, please. Okay, so at the end of the chapter, I do have like 2 or 3 slides regarding the intracellular receptors. But then this classification here is for these 5 types of receptors that we are going to talk about are surface receptors. The neurotransmitter and peptide receptors can be divided into several major groups. The first حددنا انه peptide receptor لأن usually peptides are going to يعني they are hydrophobic and in fact they are going to act at the surface receptors. The first includes the so-called serpentine or 7 transmembrane domain receptors. لكن هون في عندي عم بحكي عن 7 transmembrane domain receptor واللي هن G protein coupled receptor. You can put next to one GPCR, G protein coupled receptors. These receptors each contain an amino terminal extracellular domain followed by 7 hydrophobic amino acid segments, each of which is believed to span the membrane bilayer. يعني في عندهم 7 hydrophobic transmembrane segments. The 7th of these, in turn, is followed by a hydrophilic carboxyl terminal domain that resides within the cytoplasmic compartment. As a group, they share a dependence on the G protein transducers to execute many of their biological effects. As their name suggests, they are G protein coupled receptors because of their dependence of the G protein transducer. If we look on this type of receptor, we have this here a figure on this slide that shows you the different types of receptors, the 5 types of receptors that we are going to talk about. So each time I will come to this slide. So here you have the serpentine because it's having 1, 2, 3, 4, 5, 6, 7 transmembrane segments. Its N-terminal side is glycosylated, as you can see by this small Y in black. And this is its N-terminal side that is usually extracellular. And then the 7 transmembrane passages. And then you have a C-terminal domain, which is much more hydrophilic, which is going to be inside of the cell, and it is cytoplasmic. 7 transmembrane domain receptor. Example, beta-adrenergic catecholamines are hormones that are going to bind to this type of receptor. Second type of receptor includes the single transmembrane domain receptors that harbor intrinsic tyrosine kinase activity. You can put next to them TKR for tyrosine kinase receptors. Okay, لكن هون قلنا GPCR, هون TKR for tyrosine kinase receptors. And also we talked already about this type of receptors that have an enzymatic activity that is intrinsic to the receptor itself. So the receptor is playing the role of of recognition and binding at the same time that it has a catalytic activity. They are single transmembrane domain receptors. They have the catalytic activity. Examples, the insulin receptor, the IGF receptor, and EGF receptor. All three of these ligands have the same type of receptor, which is TKR. If we go together to the slides and we look at a tiny type of receptor, you can see that it is a one transmembrane passage. It, of course, will have an N-terminal domain and a C-terminal domain. And in its cytoplasmic domain, you can find a tyrosine kinase domain, which is a domain that has a catalytic activity and that is able to phosphorylate the tyrosine residues of the receptor and of other molecules. We will see later on with more details. The third type of receptor, excuse me, which is functionally similar to the second group. Okay, these receptors do not possess intrinsic tyrosine kinase activity, but then they function through interaction with the soluble transducer molecules, which do possess such activity. So we are going to call them receptors that are coupled to tyrosine kinase activity, or you can call them TKCR, please. You put here TKCR for tyrosine kinase coupled receptors. Okay, لكن صار في عندي GPCR, TKR, and TKCR for tyrosine kinase coupled receptors. So بس كلمة coupled بتفرق بينهم وبين ال family number 2. Both of them are going to induce a kinase activity, in particular a tyrosine kinase activity inside of the cell. But the difference is that the tyrosine kinase here is going to be soluble. It's not intrinsic to the receptor itself. يعني الريسبتور ما بيقدر يكون عنده هو بنفسه an enzyme بهيدي الحالة. Whilst in the second group, TKRs, they do have the catalytic activity in the receptor itself. Example of hormones that are going to have such type of receptor, tyrosine kinase coupled receptors, and prolactin and the growth hormone. The fourth group is, let me just show you the third one before I go to the fourth. So here, as you can see, كمان one transmembrane passage, one transmembrane passage, yes, okay. And it is for the prolactin, as I said, and for growth hormone. And as you can see, it's going to be associated with a tyrosine kinase protein, accessory protein with tyrosine kinase domain. This is the protein that will give me the enzymatic activity of tyrosine kinase. Okay. Usually these receptors are مثل ما قلنا growth hormone, prolactin, but كمان معروفين كتير إنه هن receptors للcytokines. Okay, here is this one is مثل ما قلت is insulin growth factor and epidermal growth factor EGF for a lot of growth factors يعني do have TKR. The fourth type of receptor is also having an enzymatic activity, but it's not a tyrosine kinase, it's a serine threonine kinase activity. So let me take you to the fourth type of receptor. Another group are the transforming growth factor beta family members, which signal through serine threonine kinase domains in their cytoplasmic tails. Okay, لكن هون في عندي group of receptors اللي هن السيرين ثريونين كاينيز. اوكي، السيرين ثريونين كاينيز يعني هون الاس تي كي ار السيرين ثريونين كاينيز receptors. And then these receptors are going to signal through an enzymatic activity by which they will phosphorylate the serine and threonine. One moment, please. Excuse me. Okay, so we come back. I was talking about the fourth type of receptors which are serine threonine kinase. donc هون كمان في عندي بقلب الريسبتور بحد ذاته نفس الموليكول هي one transmembrane passage. كمان في عندها kinase activity intrinsic to the receptor، يعني الريسبتور بحد ذاته عم يلعب الرول تبع الانزيم. but then the substrate is not going to be a tyrosine that is going to be phosphorylated, rather it's going to be a threonine or a serine that are going to be phosphorylated. So we look together at this one here, TGF-beta receptor is the typical type of receptor of this type. serine threonine kinase domain, transmembrane domain. يعني مثل إذا بالريبريزنتيشن بالشيماتيك ريبريزنتيشن هون هو ذاتها مثل الشيماتيك ريبريزنتيشن تبع تي كي ارز، بس هون بس بتذكر انه هالكاينيز اكتيفيتي هالكاتاليتيك اكتيفيتي اللي عندي اياها هون هتكون serine threonine. Of course, like with the slides coming up, we will have more details and you will see the difference between them is a big difference. Both of them are going to be working as a dimers of receptors, but in a different way. The final type of receptors that we would like to talk about of the surface receptors are the guanylyl cyclase receptors. The guanylyl cyclase receptors, a fifth group which includes the natriuretic peptide receptors, operates through activation of the particular guanylyl cyclase. So these are like less known, less famous than the others. They will operate through activation of the guanylyl cyclase. تذكروا this is resembles to the adenylyl cyclase, okay, which we usually talk about as an effector that will allow the synthesis of the cyclic AMP. هون الجوانيديل cyclase is the enzyme that will allow the synthesis of the cyclic GMP, guanine monophosphate. The cyclase is covalently attached at the carboxyl terminal portion of the ligand binding domain, and thus represents an intrinsic part of the receptor molecule. Very important that the enzymatic activity is also intrinsic to the molecule. So هو بحد ذاته الريسبتور is going to have this guanylyl cyclase activity at its carboxy terminal side. The cyclase is covalently attached at the carboxy terminal portion of the ligand binding domain and thus represent an intrinsic part of the receptor molecule. So as you can see, this is the receptor and it has a guanylyl cyclase activity. Okay, so this is the classification لهول الخمسة types of receptors. Let me talk a little bit more in details today about the G protein coupled receptors. So هون أول part حتكونوا بتعرفوها، حأمشي بسرعة. G protein coupled receptors are a large superfamily of molecules capable of responding to diverse types of ligands ranging from photons to large polypeptide hormones. Many hormones, they do have the GPCR as receptors for them. It's a large superfamily of molecules that might contain about 1,000 of receptors that are different from each other. They share overall structure features. Most notably of the structural features is their 7 transmembrane segments spanning regions connected by intracellular and extracellular loops. Let me show you the loops because we didn't look at them here. You can see I have 3 extracellular loops and 3 intracellular loops. The third one of the intracellular loops is in particular important because its interaction, this loop and the tail, the carboxy terminal part of the molecule are going to play an important role in the activation of the G protein transducer, okay, of the G protein transducer. They can share overall structure features, the 7 membrane spanning regions, and then the amino terminal connected by intracellular and extracellular loops. The amino terminal domain is extracellular. The carboxy terminal tail is cytoplasmic. They assume at least 2 conformations with differing orientations of the membrane spanning segments relative to one another. One orientation is going to be favored in the absence of an agonist ligand, يعني in the absence of the hormone. the receptor does not activate a G protein in this conformation, so that we can call it the inactive conformation when it's free from the hormone, and when the hormone is going to bind or the ligand is going to bind to the receptor, it will change of conformation, and the second orientation is going to be stabilized by the binding of the agonist ligand, and this conformation, in this conformation, the receptor is able to activate a cognate G protein active conformation is going to be called this one. All G protein coupled receptors are thought to undergo a similar conformational switch on agonist binding, producing a structural change in the cytoplasmic domain that promotes a G protein activation. So من كل هيدا بس أنا إنه بدي أعرف إنه في عندي 2 conformations للجي protein coupled receptors. Which one that is going to be called the inactive conformation when this GPCR is going to be free, not bound to the hormone, and the active conformation is going to be obtained after the binding of the hormone to the G protein coupled receptors, and by which the receptor will be able to activate a G protein inside of the cytoplasm, which will lead to the transduce the message. Now, if we talk about so here we talked about the G protein coupled receptors generalities and what is going to be common in all this wide variety of receptors. Now, if we would like to talk a little bit about the G protein transducers, يعني هي G protein اللي هي دايما إذا أنا بحكي GPCR, so of course I need to talk about the G protein. G protein, you already know them, are a family of heterotrimeric proteins that regulate the activity of effector molecules such as enzymes, ion channels, resulting ultimately in biological responses. Don't forget that G proteins are a big family where I have the big G proteins and the small G proteins. وهون الجي بروتينز اللي بيكونوا coupled على receptors هن البيج جي بروتينز اللي هن heterotrimeric مؤلفين. heterotrimeric يعني مؤلفين من 3 subunits that are different from each other يلي هن usually are called alpha, beta and gamma subunits. So the G proteins coupled to the receptors are from the big from the family of the big G proteins, which are heterotrimeric, that regulate the activity of effector molecules such as enzymes or channels. نتذكر سوا انه الجي الفا stimulatory هتعمل activation, it will regulate the activity of the effector, which is adenylyl cyclase, resulting ultimately in biological responses. The identity of the G protein is defined by the nature of its alpha subunit, which is largely responsible for effector activation. الجي protein الايدنتيتي تبعها is going to depend on its alpha subunit in particular. يعني أنا I can do a classification in G proteins depending on their alpha subunits, which is largely responsible for effector activation. يعني mainly the alpha subunit is the active subunit. The major G proteins involved in hormone activity and their actions are GS for G alpha stimulatory, GI for G alpha inhibitory, and G alpha Q, G alpha Q, which is going to stimulate the phospholipase C. You remember all these? You will have, يعني you will remember them هيدا شوي. G alpha stimulatory is that when the G alpha is stimulatory هيدا type, it's going to stimulate الادينيليل cyclase. يعني الادينيليل cyclase بهالحالة هو الإفكتور. G alpha inhibitory, it will inhibit الادينيليل cyclase. ما شايفين فيها تعمل لها stimulation, فيها تعمل لها inhibition. So it's going to regulate هيدي it regulates the activity لها الإفكتور, which is the adenylyl cyclase in this case. But when the G protein is a G alpha Q, then it's going to stimulate another effector, and in this case it's going to be the phospholipase C, which is an enzyme able to cleave the phospholipids. Okay, يلي هو it will cleave, for example, PIP2, if you remember, phospholipase. Now let's see the rest of the G protein heterotrimeric complex. The beta and gamma subunits of the G protein are tightly associated with one another and function as a dimer. In some cases, the beta gamma subunit dimer also regulates effector functions. يعني in rare cases, البeta والgamma, they might also have a role in the regulation of the effector, but usually the alpha subunit is the one that is responsible of the regulation of the effector. G proteins are then covalently tethered to the plasma membrane and are thus proximate to their cognate receptors and to their effector targets. You know what? Just put that the G proteins are proximate to their cognate receptor and to their effector targets. Just this, because here it's not like very clear. بهيدي السنتنس I don't want you to be confused. هلا you will see in the figure إنه ال G proteins different subunits منهم هن معلقين بالبلازما membrane through prenylation and it's يعني of course they are peripheral منهم integral protein على ال membrane, they are peripheral but they are peripheral يعني they are anchored to the plasma membrane. They are anchored through prenylation. Okay, هلا you will see. So بس حطوا هون please إنه G proteins are proximate to their cognate receptors and to their effector targets. There are about a dozen different G protein alpha subunits and hundreds of distinct G protein coupled receptors. تخيلوا أنا في عندي ميات من ال different distinct G protein GPCR عندي منهم من الميات بس عندي بس تقريبا a dozen 12 different G alpha subunit بالG protein. So this means that a particular G protein is going to be activated by a large number of different receptors. يعني G alpha stimulatory ما مش انه والله واحد type of receptor GPCR رح يعمل activation للجي الفا stimulatory. لا، حتشوفوا انه جي الفا stimulatory حتلاقوها بالبيتا ادرينرجيك ريسبتورز، حتلاقوها يعني بالكاتيكولامينز، حتلاقوها بعده other types of receptors انه حيكون عندي الفا اس. دونك بس اللي هون الفكره من هذا الموضوع انه it's not like كل جي بي سي ار عنده الفا that is different، جي بروتين تبعه الالفا تبعها different. لا، particular G protein is activated by a large number of different receptors. Example, G alpha S is activated by receptor for ligands as diverse as beta adrenergic catecholamines. يعني الابينفرين والابينفرين والنورابينفرين they can activate G alpha stimulatory. Okay, and large polypeptide hormones such as LH, luteinizing hormone. Okay, this is of course very different from the catecholamines. كمان it's going to activate G alpha stimulatory in its target tissue. LH is thereby able to stimulate adenylyl cyclase and raise intracellular levels of cyclic AMP that express LH receptors such as Leydig cells of the testis. يعني بالليديك cells of the testis I do have a GPCR that has an alpha stimulatory, and then when the LH is going to bind to its receptor, it's going to activate the alpha S, which will activate adenylyl cyclase and increase cyclic AMP in these cells. Okay, now this is a schematic view of the sequence of events that are going to be taking place, and on the next two slides you will have all the sequence of events. No, one slide. You have the 4 steps of these, what's happening. So let's go together first and the schematic view, and then we read the slide. Okay, so let's try to start from here, the complex, the hormone and its receptor GPCR that is going to activate alpha beta gamma, which you can see, which is the G protein. So at the initial situation, the G protein is going to be in its inactive form, where the alpha subunit, it harbors a GDP, guanosine diphosphate. الجوانوزين diphosphate مع الألفا بتكون معلقة بالبيتا والجاما. Altogether this complex is in its inactive conformation. This is the inactive conformation. Once the hormone binds to its receptor, then this will lead to a change a little bit in the conformation of the receptor from an inactive conformation to the active conformation اللي حكينا عنها هلا بعدنا من شويه، اللي هي بتغير الاورينتيشن تبع membrane spanning segments inside of the membrane. This will lead to changes in the conformation, the C-terminal domain مع third loop تبع receptors, which will lead to the activation of the G protein. And the activation of يعني هون بصير في عندي interaction بين الريسبتور والالفا سب يونت، وهالانتراكشن يلي عم تحصل هون بتغير كمان من الكونفورميشن تبع الالفا سب يونت, which will lead in fact to the dissociation of the GDP. Okay, GDP is going to be released and it's going to be replaced by GTP, and the GTP concentration of the GTP in the cytoplasm is higher than the concentration of the GDP. So it's going to be replaced by GTP. Now, when I do have alpha GTP, the alpha subunits is going to be dissociated from the whole complex, but in particular is going to be dissociated from the beta gamma complex, the other two يعني subunits. The other two subunits are going to be dissociated from the alpha that is the active part now. Of course, the hormone is going to be released from its receptor لأنه this is a reversible interaction, and don't forget إنه الهرمون رح يطول كتير بالدم, is going to be decreased in its concentration, while receptor is going to go back to its initial conformation, which is the inactive one. But the message has been arriving to the cell, and the alpha changed its conformation, alpha subunit, and is now going to activate its effector. So the effector مع alpha that is active is going to be activate the effector, which can be bon هلا بناخذ لما نحكي عن اثنين effectors الادينيديل سايكليز او الفوسفوليبيز C. اوكي, الادينيديل سايكليز الافكتور بيصير مثلا activated, then I will have for example a phosphorylation. اوكي, adenylyl cyclase بدي تعطيني sorry cyclic AMP, and then it will lead to phosphorylation and so on. But the alpha GTP is not going to be remained in this conformation for long. So this is also an intrinsic capacity or ability of the G protein to hydrolyze the GTP into GDP. The GTP is going to be hydrolyzed. So this is the phosphate of the GTP in fact, and it's going to be hydrolyzed into GDP. والالفا GDP بترجع بتتحد, it reassociates with the beta and gamma in order to give me the inactive G protein. So this is the cycle of an activation by G protein coupled receptors that is going to activate a G protein. As you can see, this G protein passed from alpha GDP, in which it is a heterotrimeric and inactive, to an alpha GTP, where it's going to dissociate from the rest of the complex and is the active form, after which there is an intrinsic catalytic activity by which it's going to hydrolyze the GTP into GDP, and all the system is going to be brought back to the initial state. All this is written here in this slide, so I will go a little bit rapidly because I already explained it. In the basal inactive state, the G protein is an intact heterotrimer with guanosine diphosphate bound to the alpha subunit. Agonist binding, يعني hormone binding to the GPCR, promotes the physical interaction between the receptor and the G protein. This produces a conformational change in the G protein, resulting in the dissociation of the GDP. So I have what I call an exchange. Very important please. إنه هون مش عندي reaction عم بتصير عم بتحولها من GDP ل GDP. It's an exchange. GDP عم تطلع عم تيجي محل GTP, which allows the binding of GTP that is present in a much higher concentration in the cell than GDP to the alpha subunit. Now, the dissociation of GTP bound alpha subunit from the beta gamma dimer بصير في عندي تفرقة بهالجي protein between the subunits. It occurs allowing these subunits to activate the effector target. Dissociation of the hormone receptor complex also occurs. No more need for the hormone to be bound to the receptor. Anyhow, the concentration of the hormone is going to be reduced in the blood very rapidly. The duration of activation is determined by the intrinsic GTPase activity of the G protein alpha subunit. مثل ما قلت هالجي alpha subunit كل الوقت هي عم تعمل stimulation للإفكتور اللي هو مثلا adenylyl cyclase. كل ما هي عندها GTP بس ولكن في عندي هالactivity is intrinsic. هالduration رح تكون متعلقة بالintrinsic GTPase activity which will hydrolyze the GTP into GDP, which will terminate the activity and promotes reassociation of the alpha beta gamma trimer, returning the system to the basal state. The GTPase activity of G protein alpha subunits can be increased by the action of proteins termed regulators of G protein signaling, which are RGS proteins. So just هون هيدي الملاحظة يلي هي بالأحمر هي in order to say إنه مزبوط نحن قلنا إنه the GTPase activity تبع الجي بروتين is intrinsic, هي من جوا بتطلع بتعمل hydrolysis, but sometimes it can be helped or it can be increased or stimulated by the activity of some other proteins called regulators of G protein signaling. If you remember كنا نحكي عنهم GEF يلي هو G protein exchange factor والجي تي بيز اللي بيعمل اكتيفيشن للهيدروليسيس اكتيفيتي. اوكي اللي كنا نسميه الجاب كنا نسميه الجي اي اف والجي اي بي. اوكي جي اي اف فور جي بروتين اكسشينج فاكتور والجاب is for G protein activating protein that will activate يعني the hydrolysis. I will just talk about the first effector, adenylyl cyclase, and we leave the other for next time. So the first effector that I would like to talk about is adenylyl cyclase, which is an enzyme that is going to be embedded in the plasma membrane. Okay, integral. Numerous effectors have been linked to the G protein coupled receptors, GPCRs. Adenylyl cyclase perhaps is the best studied of the group, and it's going to be activated by G alpha S for G alpha stimulatory. This activation results in a transient increase in intracellular cyclic AMP levels because the enzyme adenylyl cyclase is catalyzing the transformation of ATP into cyclic AMP. The cyclic AMP binds to the inhibitory regulatory subunit of inactive protein kinase A and promotes its dissociation from the complex, thereby permitting enhanced activity of the catalytic subunit. Each time when I have, for example, a second messenger such as the cyclic AMP here that is going to be increased in the cell, this will lead to an activation of a kinase. In this case, where the second messenger is a cyclic AMP, the kinase is going to be called PKA, protein kinase A. Okay, so has cyclic AMP رح يقعد it binds to the inhibitory regulatory subunit. في عندي إذا ما كان عندي عالي الcyclic AMP في عندي بهالبروتين kinase A subunit that is inhibitory regulatory, يعني وجودها بيعمل inhibition لهالبروتين kinase. cyclic AMP بيعلق على هالinhibitory regulatory subunit and it's going to promote its dissociation بيزيحها عن PKA, and so the PKA is going to be active, permitting enhanced activity of the catalytic subunit. Let's see this here. Maybe it is going to be clear on the figures. So first, as you can see here, I have a receptor. This is in pink. This is my GPCR. And the adrenaline is my hormone. that is going to recognize and bind to the GPCR. Of course هون الcytoplasmic tail تبع هيدا الريسبتور is going to be in close proximity to the heterotrimeric G protein. And بهيدي الرسمة هون شايفين إنه in orange is the alpha subunit while in blue and green are the beta gamma subunits. This is complex. Now I do have a binding to the alpha subunit, a binding domain that will bind to the GDP. As you can see, this is the inactive conformation of my G protein. Once I have the binding of the receptor, of the hormone to the receptor, it will in fact interact with the alpha subunit here, making a change in its conformation, which will lead to the replacement of the GDP by a GTP. And when I have this replacement, this alpha subunit in orange will dissociate from the rest, which is beta gamma that you can see here, dissociated beta gamma subunits. And this active subunit is going to move a little bit in the membrane in order to come and bind to adenylyl cyclase. Adenylyl cyclase is embedded in the plasma membrane with its catalytic activity acting in the cytoplasmic domain. Once it's activated by G protein, it will in fact allow the formation of cyclic AMP from ATP. And now my cyclic AMP is going to be increased in the cell. This is my second messenger. What is my cyclic AMP going to be doing in the cell? Look at this nice figure here. From the beginning, you can take this is the receptor, this is the GS, alpha S, adenylyl cyclase activated. From the ATP is going to give me cyclic AMP. I arrived here. What do I have? I have an increase in my second messenger cyclic AMP. Cyclic AMP is going to activate PKA. هيدي ال PKA. It's like regulatory subunits وهيدي الراوند هي الانزيماتيك activity اللي بتعمل فيها phosphorylation protein kinase A. هيدي regulatory subunit that is going to inhibit the PKA. Once the cyclic AMP binds to it, it's going to remove it from the PKA, and then my catalytic activity is going to be active. PKA phosphorylates cytosolic enzymes such as phosphorylase kinase. An example is the phosphorylase kinase that is going to be activated by by PKA. But this is not the only role of my protein kinase A. It might also be translocated into the nucleus, where it's going to phosphorylate other proteins such as the ones that we call CREB, okay, and like that are represented in a dimer, homodimer. Once phosphorylated, this CREB is becoming an active transcription factor and is able to bind to the Cre consensus sequence for cyclic AMP response element binding a protein. CREB هو for cyclic AMP response element binding protein. So what does this mean? It means that it is a transcription factor that is able to be activated by the cyclic AMP, and that is going to bind to the consensus sequences that have specific response to the cyclic AMP. Okay, so it's depicted bound to a consensus Cre in the basal state for cyclic AMP response elements. Cyclic AMP response elements. So I go back to my slide where I arrived here. PKA phosphorylates a variety of cellular substrates, among them the hepatic phosphorylase kinase. يعني ممكن أنا تعمل لي phosphorylation للhepatic phosphorylase kinase that initiates the enzymatic cascade, which results in enhanced glycogenolysis. وهيك بيكون هالابينفرين اشتغل شغله بالهيباتيك سيلز فور اكزامبل على السيكليك اي ام بي، راح اشتغلت على البي كي اي. هالبي كي اي راحت عملت فوسفوريليشن لانزيم موجوده بالهيباتوسايتس اسمها الفوسفوريليز كاينيز، ويلي هي راح تشتغل على الجلايكوجين in order to تعملي glycogenolysis لحتى احول هالجلايكوجين لجلوكوز. Good, but as I said, this is not the only function of my cyclic AMP. It also can activate the CRAB. Okay, it also phosphorylates and activates the cyclic AMP response element binding protein CRAB, which mediates many of the known transcriptional responses to cyclic AMP and to some extent calcium. In the nuclear compartment, other transcription factors are also known to be phosphorylated by pKa. As you can see, pKa not only phosphorylates enzymes in the cytoplasm in order to change metabolic pathways, but also can, in fact, phosphorylate some transcription factors in the nucleus and induce a change in the transcription in the cell. Okay, I will stop here today, and the rest, hopefully, we will finish it in one session, or if not, we will take 2 more sessions to finish this chapter. What questions do you have regarding this part? Any questions? Hello?
Doctor?
Yeah, one moment. Muhammad Hamoud, you were not able to hear? Are you here? Is he with us? Unmute the speaker, unmute the microphone. But you others are able to hear me, right?
Yes دكتور هي
يلا مين بده يسألني question؟
دكتور بس كان بدي أسألك سؤال بالنسبة للجي بروتين ريسبتور.
يا
حكيتي إنه إلهم 3 intracellular لوب، واحد منهم عنده important role، شو هي؟
يا اللوبس يس بالجي بروتين كابلد ريسبتورز مثل ما قلنا في عندي 3 لوبس برا و3 لوبس جوا. ثالث واحد من الجوانيات اللي هو قريب على السي تيرمينال سايت تبع البروتين تبع الجي بي سي ار عنده رول مهم بالاكتيفيشن. يعني هون بنرجع بنحكي عن الكونفورميشن. ما تنسي انه انا قلت انه الجي بي سي ار بيمرق من ان اكتيف كونفورميشن لما ما بيكون باوند على الهرمون على اللايجند تبعه، وبيمرق على الاكتيف سايت. هالتشينج بالكونفورميشن بيغير كونفورميشن لكثير اشياء، منهم السباننج، الاورينتيشن تبع السباننج، السبعه سباننج ترانس ممبرين سيجمنتس، وكمان من اهمهم هي الثالث لوب الانتراسيلولار لوب، لانه تلعب رول هي مع السي تيرمينال سايت بالاكتيفيشن للجي بروتين. يعني بالنهايه انت عم تتخيلي انه شغلتين قريبين من بعض، الجي بروتين قريبه والجي بي سي ار قريب. اوكي، الجي بي سي ار موجود بالممبرين، والثاني الباقيين موجودين سيتوبلازميك. يعني عندي السيتوبلازميك هي الجي بروتين، اوكي، والترمينال سايد السي ترمينال سايد تبع الجي بي سي ار. هون بده يصير في عندي انتر اكشن بيناتهم، بين ما اذا كان هو الجي بي سي ار ان اكتف او اكتف، بده يصير في تغيير. اوكي، وهالتغيير not only put التيل سي تيل تبع الجي بي سي ار in play, but also the third loop of the GPCR. ما بعرف إذا وصلت لك.
Okay, doctor, thank you.
يا جهاد. Doctor, where is the presentation of this? I cannot find it. So waiting here. One moment. Maybe here it doesn't show. يعني في عندي a figure. Maybe the first figure there. The classification. Where's the classification of the receptors? Yeah, here. You see what I'm talking about, Jihad? This C-terminal side here and this third loop, هي third loop أكبر من هوليك اللوبس، والسي terminal side هو اثنين they will interact. هن أقرب شيء للجي بروتين. الجي بروتين حتكون هون، بس ما في interaction بيناتهم إذا كان هيدا الجي بي سي آر منه occupied. ما في interaction، ما لازم يكون في عندي interaction. هالinteraction بدها تحصل بس يصير هو occupied by a hormone. هيدي اللوب مع السي terminal اثنيناتهم هيشتغلوا in order to activate الجي بروتين بطريقة إنه change of conformation وبيقتربوا منها للجي بروتين which will lead to a change in the conformation of the alpha stimulatory. Yes.
Okay, doctor, thank you.
Doctor,
Yes, yes.
two
Who
pathways
else?
في PKA enzyme مش
Sorry
دايما
for
بتصير صح؟
ما عم بسمعك. Sorry ما عم بسمعك.
هلا أحسن؟
Go ahead.
The two pathways of the PKA enzyme مش دايما بيصيروا حسب الهرمون اللي عامل binding صح؟
Are you asking me about what different enzymes are going to be activated in the target cells?
No, the PKA enzyme مش يا بتعمل phosphorylation يا بتغير الترانسكريبشن فاكتور.
Yes, PKA, right. It's a protein kinase. Yes.
Yes. أي pathway بتاخد حسب الهرمون اللي عامل binding على الريسبتور؟
Good question يا فاطمة. Yes, it's not only حسب الهرمون اللي عمل binding، حسب أكثر التارجت سيل. التارجت سيل تبعك إذا هي هيباتوسايت، انتبه إنه هالهرمون هي موجودة بتعمل activation لعدة تارجت سيلز. Right?
Yes.
إذا كان هالتارجت سيل تبعك هيباتوسايت فيها هيدي الإنزيم يلي هي الجلايكوجين فوسفوريليز. اوكي. اما اذا كنت بمحل ثاني سيل ثانيه تارجت ثانيه ما في عندها هيدي الانزيم وبالتالي طبعا مش رح تصير activated. طبعا هيدا الشيء لكن it depends on the target cell itself.
Okay, thank you.
You are welcome. Any questions? No, so I will stop the share and see you next week inshallah, okay, to continue the chapter.